Good, okay. Okay, let's do it, guys. So, a lot of energy in the room, yeah. All right, let's start. So last time we talked a bit about, well, I said robust and stochastic control. And I really only got through the stochastic part of it, or a few ideas from the robust stochastic part of it. Although I mentioned kind of, I gave you the restaurant menu of all the types of different things we could be talking about in this space. We spent most of our time here. In particular, we looked at, for instance, stochastic LQR. Remember we did the UAV in the wind example, where stochastic LQR, even though the big result in stochastic LQR in some sense is that deterministic LQR is still the right answer. But the UAV was an example of showing you how you could take a non-Gaussian process, turn it into a Gaussian process, and it actually does justify using a different controller in order to stabilize that, one that estimated the state of the wind. We talked briefly about stochastic trajectory optimization. Okay, so today, the natural thing that I'd like to do is to try to do roughly a little bit of robust LQR, which goes by many names. H2, there's an H2 version of this, there's an H infinity version of this. I'll do H infinity, a particular form of H infinity control. And we can talk about robust trajectory optimization. But really, the ideas and the tools are not specific to LQR or trajectory, or not so narrow as LQR and trajectory optimization, right? The big ideas of this are, in stochastic control, have been thinking of, I mean, in both cases, it's thinking about distributions evolving over time. In stochastic control, we typically use the expected value or some sort of scalar objectives on the random variables, right? And we can do that in any of our favorite problem settings. And then in the robust control, we try to give some sort of maybe worst case guarantees or bounded, make less assumptions about the distributions and try to give a guarantee saying that the performance will be at least some, have some strong properties. But because we kind of did the stochastic LQR last time, it opened the door for me to make one more connection that I really want to start with. Let me tell you a little bit about how stochastic LQR helps us think about policy search. So let's say, if you think about all the results from control theory that we have, and I think I've just given you a taste, but I think hopefully you'll see that in systems theory and control theory, there's just lots of really deep understanding of and guarantees and theorems and super strong results. And we have also empirically incredibly good success in reinforcement learning. And one of the big things that I think is great happening in the world right now and that I'm super excited about is sort of trying to pull control theory towards reinforcement learning and bring reinforcement learning towards control theory a little bit. They have lots, they're solving the same problems, okay? And really, we got a little bit closer to this last time than we ever had before because stochastic formulations and expected value costs that is the dominant language in reinforcement learning. Okay, so let's just see if we can learn a little bit or think a little bit about that connection through the lens of stochastic LQR, and then we'll come back and spend the second half doing that. So we've talked about LQR many times in many different ways. That's intentional. It's not annoying. But one of the first things I said about LQR, right, was that, you know, one of the first things I said is if you're searching directly in K, if you're just changing feedback gains, then that's a kind of a nasty space potentially to operate in, that I could change K a little bit and my system could go from stable to unstable, for instance. And LQR is actually pretty different, where if I just search in the, you know, positive definite matrices Q and R, then that's a way for me to express my preference, but every choice of Q and R is going to give me a stabilizing K if the system is stabilizable. Yeah? So that was like my initial motivation, right? And then we saw that we know how to do, we try to find these Ks using the same Q and R even in the stochastic control. In reinforcement learning, though, people aren't solving Riccati equations. They're not doing this typically, right? They're searching directly in K. So that sounds, I had set that up initially as like a bad idea, right? It turns out it's not quite as bad as you might think. Relatively surprisingly, it's not quite as bad as you might think. And the stochastic LQR derivation we did last time gives us a way to sort of see that, and maybe just a window into what's happening kind of in some of this intersection between learning theory and control theory, okay? So let me just tell you a little bit about what we can understand about searching directly, doing gradient descent directly in K in a stochastic LQR setting. Okay, so if the so goal is to do policy search, policy gradient, let's say. So I'm going to try to do gradient descent, e.g., so I'm going to try to take the with respect to K and see if we can study that at all right, and understand anything about it. But in particular, we're going to do the stochastic control version of that. All right, so if my performance objective is this, okay, let me just be precise here. That only makes sense if I have defined the dynamics, right? If I've defined the initial conditions, I'm going to say the initial conditions are drawn from some, I'll even make it a Gaussian here. That's what we're going to use here. Some Gaussian distribution with mean 0 and covariance, just call it omega for today. So this is a normal distribution with mean covariance, okay? And I'd like to say that I'm going to choose u equals negative kx. And I want to know, first of all, if I give you k, can you tell me what the cost is going to be? That's called policy evaluation. That's just evaluating this, but I want to evaluate it, the expected value, not just one rollout. And then second, can I take the gradient of this performance metric with respect to k, and can I say anything about it? Okay, that turns out to have been turned into a fruitful topic in the last couple of years, and it's, I think I can tell you the basic story quickly enough. Is that setup clear? Please.
Yeah, could you review the motivation for searching the K? Could you just review the motivation for searching the K?
For searching in K, okay. The only motivation I gave is that people are doing this in reinforcement learning. Reinforcement learning seems to work well often. It doesn't always work. So I think in problems where we know good solutions, it makes sense to see, would reinforcement learning work? Is it guaranteed to work in this setting? Is it getting lucky? You know, and trying to understand sort of the space of problems where we think RL is going to work and where it isn't going to work. So we know a lot about LQR. Can we say, well, if this is like an oversimplified version of reinforcement learning, but we can ask, does this version, like a pure form of reinforcement learning, work in our stochastic LQR setting? Okay, so the mechanics are actually pretty beautiful. To see that, first we'll just do a little bit of manipulation on the cost function here. So I'm going to write out the cost now in terms of the feedback gains. Okay, this is just the inside of the cost function, but with the k, feedback k inserted. I'm going to group the terms here. And then there's a trick that happens a lot of times in these problems. It's worth seeing it. So this is a matrix equation, but of course the result is a scalar, right? This is a vector transpose vector. So the result of this is a scalar. The objective is always a scalar. So I can take the trace of a scalar. It's still the same value. The trace of a matrix is just the sum of the diagonal elements, and trivially the trace of a scalar is just the scalar. But the trace has nice properties where you can rearrange, you can cycle the elements, through matrix multiplication. So this is equal to the trace of Q plus K transpose X transpose. So under matrix multiplication, I can move the X transpose over here, and the trace of this matrix is going to be the same as the trace of this matrix. So this is just a different way to write the same objective. The reason to do that is that now I can write the expected value of X transpose QX I can use the properties of expected value coming inside the integral and actually even coming inside the trace to write that this is actually the trace of Q plus Q trans, I won't say it out loud, I'll say the wrong thing here. Bless you. Okay, using our sort of known properties, I can rewrite the cost function like this. And importantly, I can just group all of the terms that are random here, and that captures, that's the only thing I have to worry about for the expected value. This is just a modifier on the expected value of this thing. Okay, that's a key idea. That's actually just a key quantity in linear systems theory, is thinking about the sort of state covariance integrated over time. It's like the, yeah.
Sorry, should that be the trace of XX transpose? Right now it's matrix value.
I took the trace over here, yeah?
Oh, the trace of the whole thing.
Yeah. Yeah, so this is an important object that shows up in a lot of systems theory. It's related to the system Gramians and the controllability Gramians and the like, okay? So it's not surprising to see this emerge in our LQR cost function, okay? And people, because of this, people actually know a lot about how to compute that. It turns out there's a beautiful closed form solution for this. It's the solution of a Lyapunov equation. Just, it's almost always, these things have, these are quadratic forms. They tend to fall out as either Riccati equations or Lyapunov equations. Okay, so if I call this big thing X, okay, you could think of that as somehow the expected energy in the closed loop system response or something like this, but it's the integral of this state covariance. Okay, it happens to be, I'll write the Lyapunov equation. I don't know if it's super insightful, but it turns out you can solve for that X as the solution of this Lyapunov equation. Oops, It's okay. And so it's not quite closed form, but it's numerically it's almost closed form, right? I can solve this for the symmetric x. So let's just take a second. Yeah, please.
What's the difference between the Lyapunov equation and a Riccati equation again?
Yep. So the Lyapunov equation is it's the one we originally wrote was P A plus A transpose P equals negative Q. That's the simplest Lyapunov equation, and we're solving for P. So it's actually a linear matrix equation of a particular form. It's kind of like, you know, you have your table of possible equations that you know have solutions for, right? You know, if you're trying to integrate different functions or whatever. This one is like if you can put it into this form, then you can call a solver for Lyapunov equations and it'll tell you what P is, right? And the Riccati equation is actually a quadratic form in the decision variables. You get S transpose S. So it doesn't fit in the Lyapunov form. It's a slightly richer form, but still has good closed form solutions. Yeah. Yes?
And I guess, like, does it matter that we've framed our uncertainty or our stochasticity in uncertainty about, like, initial conditions?
Good. Yeah. So it gets slightly richer if you put in process noise also, but it would look very similar actually. Yeah. This was the minimal version of it. Yeah. Okay, but let's take a minute to appreciate what's happened here through the magic of Lyapunov, slightly uninsightful writing of the Lyapunov equation on the board. Sorry that just kind of jumped to that, but compared to most of the things we're doing, even when we talked about stochastic trajectory optimization, I said there's a step in here where you have to run samples. Pick m samples, I said, right? And we're going to roll them out, take the average of that m samples as an approximation of the true expected value. Okay, this is not that. This is closed form up to the numerical precision of solving the Lyapunov equation, but this is basically, we have an exact solution for the expected value if we had perfectly pushed the Gaussian through the linear system, right? That's very powerful. We don't have to worry about, did we run enough trials, whatever. This is exact, okay? I wrote down here, summary, linear control theory is awesome. I think that's true. Okay, so when you look at this and you look at the solution, so this is, sorry, it is, X is a solution, this Lyapunov equation has a solution when K is stabilizing. Okay, so it could blow up. If K is unstable, then this won't have a solution, a positive definite symmetric solution. Okay, so it's interesting to ask, what are the set of Ks that are stable? Okay, and it turns out that there are very simple examples saying that that set is not a trivial set, even for the LQR problem. So here's a famous example. I mean, the numbers don't matter as much as just the fact that the example is simple. Okay, you don't have to work very hard to make one up. You do have to go to 3 dimensions, I think, to get a nice example of this. Okay, this is a linear system. The matrix, the closed loop system A minus BK is stable if K is K1. Okay, it's also stable if K equals K2. But the matrix K equals K1 plus K2 over 2 is unstable. So this is evidence that the set of stabilizing Ks is not actually a convex set, even for LQR. Right, so that's kind of a surprising, or it's, I don't know. The control theorists wouldn't be surprised, but maybe I was surprised. Okay, so it's a non-trivial set. And if you think about this is just about when it's stable or unstable. When does my cost go to infinity versus being a nice quadratic function? And clearly, if the places where the cost is infinity isn't even a convex set, or not is finite is not a convex set, that means my initial objective is clearly not a convex function. This is like there is no Q or R for which it's a convex function. Okay, but here's what's surprising is that it turns out that even though the set of stabilizing k's is not a convex set, people have realized relatively recently that if you do gradient descent on this objective directly in k, you will find, if you start with a stabilizing k, you will find a good solution that all local minima are global minima, right? And that even though the set is not convex, there are no local minima. This is the kind of thing we were hearing from deep learning theory for a while, right? They were saying maybe one of the reasons neural networks are amazing is because all local minima are global minima. This is not a neural network. This is as simple as it gets, but it has a similar story. And it's like I said, it's kind of starting the road between these two worlds. Okay, so the picture maybe in one picture you have in your head, you can actually understand the cost landscape pretty well. This one happens to satisfy inequalities. There's a famous PL inequality that it satisfies. So this turns out to be a quasi-convex function. If I were to plot a slice of it through a high-dimensional space, you get functions that look like, for different values of k, this would be my total, let's say my total cost, j, the expected cost, and it doesn't actually have local minima, but it's clearly not convex. If I were to take 2 points on this function and interpolate between them, it's not above the function. The function's not convex. But gradient descent can still find the right good solution. The fact that the set of stabilizing k's, like the shape in the high dimensional space, even the boundaries of the shape are not convex. Okay, but you start in it and you won't leave it by going downhill. Yeah.
Does pure gradient descent or SGD work, or do you need like momentum or something?
Even pure SGD works. Yeah, no momentum required. I should say also that actually, so you can evaluate the policy in closed form by solving, well, almost closed form by solving the Lyapunov equation. You can also take the gradients in closed form up to solving another Lyapunov equation. The gradient of this with respect to k it's a gradient of a scalar with respect to a matrix. Gives you another matrix, and that is the solution to a Lyapunov equation. It's beautiful and good. It's like kind of like what I said about the rimless wheel. Like this is the only case where you're going to be able to do everything in closed form. In RL, maybe this is almost like the only case where you just get to say everything's in closed form. We know exactly the true gradient, not some empirical approximation. We can study its landscape, and we can say, even though it's not convex, it will find the right solution. So that's pretty cool, right? And it took some amount of stochasticity actually to make that nice. It turns out you don't have to, there are also examples where we know simple control, where RL wouldn't work for simple control problems. You don't have to walk too far away from this to get one where you say gradient descent just won't solve this problem, at least not in the original parameters. So if you were to we're going to talk about output feedback next week, where you have sensor observations. You can write simple static output feedback controllers, for instance, parameterize them with k, and show that there's no chance gradient descent is going to work in those settings. So that's a very healthy and interesting, people are solving output feedback controllers with RL, but there's reasons to believe it can't always work. So understanding that space is it's just very productive and very good. That was kind of my aside at the beginning. Was that clear? Any other questions? Yeah.
So, do we know why the landscape is like that all local? There's no local minima.
So do we know why? So yes. it's funny because when this was first I was sitting next to Sasha Magretsky, who's my one of my favorite control theorists, who knows everything about these equations, right? And we saw the presentation. And they said the LQR has no. He was like, yeah, of course. You know, it had to be that way. Let's see. Why did the control theorists, I think, know that it had to be that way? Because we've known for a long time that you can write convex reformulations of LQR by changing coordinates, for instance. You can actually, there's a way to write the LQR problem as a linear matrix inequality and solve it with semi-definite programming. And the transformation from the variables k to the convex parameterization is a smooth transformation. So it could not have introduced, or it could not have undone local minima, you know. So somehow we knew that this original space wasn't convex, but we also knew it couldn't have been that bad for the smooth change of coordinates to have changed. That's one thing. Jack, who was in our group, had thought a lot about that and studied that, tried to see if that argument could be lifted to the LQG case, and the answer is almost. But actually, LQG, there's reasons that we know it's hard. There's parts of it that we can use those kind of those examples. The original, when the paper was presented by Maryam Fazel, she gave an argument using PL inequality. So you can put bounds on the gradients basically that show that are sufficient conditions to say that you're not going to have any local minima, but they work for functions that are not convex. So there are tools that will talk about these not quite convex but still no local minima. And I've written this up in the notes that are, you know, hidden notes that I didn't actually put in the link of what you should read today. Was not linking to the notes, but it was there if you looked for it. If you searched for policy search. I will fix that. Okay. So that was sort of wrapping up stochastic control. Let's talk about robust LQR, robust trajectory optimization. Get as far as we can. Again, I feel like I'm just showing you the tip of these icebergs. In particular, a lot of robust control for linear systems and linear systems plus, a very common thing would say your system is linear plus some block of things I don't understand, but you can bound those blocks. So linear system theory goes well into nonlinear systems, but there's so much known about linear systems. A lot of it is developed actually in the frequency domain, which makes it a little bit hard to penetrate if you're coming from the state space world. So I have tried to find a few examples where I could give you the result, but stay in the state space domain and give you a Riccati equation kind of interpretation. So let's think about robust control and L2 gains, okay, for LQR kind of problems. So imagine I have a linear system. Let's even just keep it I don't even need input for this yet. Let's just say I have a linear dynamical system where there's no inputs, but there's noise coming in, okay? In our best case, in our deterministic systems, we could talk about stability of these things. We could ask about x going to 0. We could come up with a Lyapunov function. We said, of course, if v of x is greater than 0, v dot of x strictly less than 0, could tell me that x is going to 0 as time goes to infinity. If w is a Gaussian, for instance, coming in, a Gaussian white noise, then clearly I'm not going to be able to find a Lyapunov function that certifies I'm going to converge to the origin as time goes to infinity. We talked about that last time. But all is not lost. It turns out a slight generalization of this can give me a different argument what I'd like to say instead is something of this form. I'd like to say something like this, okay? So let me talk that through. I could write the same thing, and maybe it's even easier to think about in discrete time. It looks the same, but look maybe easier to think about. Okay, it's still a supremum over that. So what is this thing summed over some, I could go from n equals 0 or even try to think about the infinite horizon limit of this. Okay, but this is somehow like the energy in the noise. Okay, this is somehow like the deviation, the energy in your distance from the origin. So what you'd like to say, I mean, you could maybe move this on the other side if that helps you. You'd like to say that the deviation that x is around the origin stays small relative, is like some fraction, you would like gamma to be small, some fraction of the energy that's in the original signal. So the gain from input to state, in this case, is this gamma, and it stays small. And these are the L2 gains, because I took the L2 norm of that signal, and this is suitable whenever that L2 norm is finite. Okay, so you'd like to have bounded L2 input, should confer bounded state walking around stuff, and you'd like to say that ratio is small. Okay, so even though with some small probability W could get very, very large and X could take a deviation, what we can still say, give some absolute guarantees about the ratio for linear systems. Asking for just what is X, what's the biggest X that could ever happen, is a bad question for a linear system. X could be vacuously big, right? But asking for the L2 gain is a tractable good question. And this just says I'm going to search over the worst case W, right? So this gamma is called the L2 gain. So first, to certify an L2 gain, we can adapt our Lyapunov-like arguments. It turns out a change to the Lyapunov argument can certify that a linear system of this form has an L2 gain, or any system of this form, but the Lyapunov equations flow freely in the linear system setting. I'll leave that here, and I've got one more board than normal today, so. Okay, this generalizes Lyapunov. So what I'm going to look for is a v of x greater than 0, but I want to say that v dot of x, instead of being less than 0, is less than some supply rate, which can be a function of both x and w. As you'll see, I mean, not surprisingly, this is, when we put the cost over here, remember we did a lower bound on the cost to go kind of idea? That's very related to this. But here now, W is potentially random. It's the only difference, okay? If I can find some function, I'm going to fix S. I'm going to choose S. choose some supply rate. If I can find some function here that satisfies that, I may be still, for good choices of S, I might still be able to say something useful. In particular, I mean, the key observation is if I want to integrate over some finite horizon, both the left and right side, do something like this, okay? And what's amazing is that the thing I need to prove an L2 gain is just to choose a particular supply rate to be gamma squared W squared plus, minus X squared. You can sort of see how that's going to work. So in that particular choice, then I'm going to get a gamma squared W squared minus 0 to t. Okay, if I can bound this by the initial value, let's say V, if I can bound this value, then this is enough for me to then put that on the other side and actually claim that I have a L2 gain. Yeah, I'm just reminding myself of the exact argument. So since this must be true for all x, if x0 was chosen to be 0, then I can make this thing 0. I can just drop this out, which means Vx of t has to be less than that for that particular case of starting at the origin. And since Vx of t has got to be greater than 0, we can actually just move this over completely. So this actually, so the two steps were V of x0 equals 0, since x0 equals x must work. And then we know that V of x at capital T has got to be greater than or equal to 0. So I can use that to make this bound, tell me that finding a storage function or a Lyapunov function of that type, a dissipation inequality of that type, is enough to guarantee that the integral of x squared okay, so the mechanics are there, and they're done more carefully in my notes, but which is in the book too. Okay, but a couple things happened here. So this is a generalization of the Lyapunov function in the sense that you're allowed to go uphill sometimes. Okay, so the visual you might have is that you have like a storage tank. You have a supply rate of energy coming into the tank, and you'd like to make sure that the tank only, it only goes down relative to that supply rate. So rather than just having, in the standard Lyapunov where there's no input, your tank can only leak, I guess, right? But here you're saying, I want to be leaking, except for, of course, if somebody's putting new energy in, that's okay, right? So if disturbances are putting new energy in, I have to accommodate that, and I just ask for this to hold. And it turns out, when you write your supply rate like this, then that's enough. Finding this sort of Lyapunov-like function is enough to guarantee. If you can find a V, then you've actually found an L2 gain proof. So if I decreased gamma below what the system is capable, what the true L2 gain of the system, then I would not be able to find that V. Okay? As I increase gamma, finding that V is going to be easier. But once you find any V for some choice of gamma, then you've certified the L2 gain. Is that clear? You guys don't look like you love that. Please.
I may have missed it, but what are the rules for the for the supply rate function? Like what properties?
Okay. So it has to be a function of x and w here, but in order to have this, this hold. But what's interesting really is for particular choices of s, then you're allowed to, then you can make particular statements about the long-term performance. So actually, dissipation inequalities are a general concept. There are a handful of canonical choices for S that give you different properties about the system. I showed you the L2 gain one. There's other things you could say via choosing different supply rates. Okay, but they all go through this basic argument that the total integral of the supply is going to be less than the difference in my Lyapunov-like function. Okay, and if that's enough for you to give some strong property out, then it's useful. So it's not typically that you search over S. It's the designer comes in and says, if I search over V that satisfies this type of supply rate equation, then I've obtained some guarantee. Yeah.
Sorry. I think I missed your explanation. Would you mind explaining again what the L2 gain is saying about the system?
Sure. So think about, I've got some amount of energy coming in. It's too much to say that x is going to go to 0. We don't expect x to go to 0. What we're asking is that the deviations of x from 0 are small, proportional to the deviation, the energy that's coming in. The energy of x walking around 0, the smaller the w is, the smaller x would have to be. It's proportionally small. But if someone comes in with a huge signal of a huge amount of disturbances, then I admit that x is going to be potentially big. The total energy in x. It's a gain bound instead of a absolute bound. You cannot say that x will stay inside -1 and 1 or something like this, but you can say proportionally it'll stay inside. Yeah.
Is there an intuitive interpretation of why the supply rate is a function of state, and not just like
The way I said it, I can see why you say, the supply is just W, right? But I mean, the mechanics, of course, kind of work out if I allow myself, and it's more expressive if you say that if you allow them to be coupled, that energy put in a current particular state counts differently than something I put in, at x0 might count differently than, so it sort of seems reasonable to me to allow them to be coupled. And algebraically, this gives us this nice result, and I would say many of the supply rate arguments require both. So that's like 4 different almost answers, but that's what I've got. Yeah. Okay, so think about a storage tank, right, where you're putting the supply in, you're still leaking down, and you just try to say something about the rate that it's going down, okay? So this is cool. So now if we can do an LQR derivation that can sort of find the smallest gamma, then we've done something interesting, right? Like I want to find a k to push gamma down small. It turns out, I want to make sure I say dissipation inequalities are actually, an important generalization of Lyapunov, not only because they allow randomness in, but you can actually use dissipation inequalities to talk about the output too. So Lyapunov functions were only about state stability. They're talking about what x is doing. Dissipation inequalities can talk about input-output stability. Okay, so let me just say that. So more generally, let's say I have W coming in. Oftentimes we use Z for this coming out, okay? And I want to talk about somehow the input-output gain. So if I want to talk about the magnitude of the signal of Z squared relative to the magnitude of W, that would be a similar argument here. You can talk about the input-output L2 gain. That's actually the more common one. Okay, supremum and everything, right? And this becomes incredibly important when we want to start doing composition of multiple systems. If you can say, for instance, I've got many systems in a block diagram, but the L2 gain of here has, there's some L2 gain here, I've got some L2 gain here, and some L2 gain here. I can compose my input-output bounds into an L2 gain for the whole system. Okay, and the most important and most famous of that is if you actually have a feedback combination. If you do something like this, if you have an L2 gain of this system from here to here, and an L2 gain of this system from here to here, then you can actually recover deterministic stability if the L2 gains, the loop gain is less than 1, basically. Okay, that's there are small gain theorems that talk about composition. About feedback composition of L2 gains. Okay, so the fact that you can sort of use this machinery to talk about input-output gives you this power to do connections. I'm not really saying enough, but just to tell you that there's a whole world out there of doing compositional verification, for instance. People often say things like, oh, we really, it happens in neural networks, it happens whatever, like, we really need to think about how to do compositional verification. No one's ever thought of that before. And it's, we have a lot of work to do, but there is, it's the famous thing that has happened in control theory for a long, long time. That's why block diagrams are so powerful. It's that we can make sweeping statements with these kind of theorems. Sorry.
The W on the left is additive, it's summing into that?
So you could have additional inputs and then ask about the stability of you could ask about the total input-output gain of a feedback system if you were to do something like that. But the simpler statement I made was if I just have a feedback combination of systems, then that system will converge deterministically.
Because I'm asking, the W is additive noise to whatever signal
Okay.
you actually care about? Or
Good. So I went too fast on that. So here's the standard picture. Let's just say I have X, and I'm designing some sort of controller here. Let's say my plant is actually not linear, okay? But I could approximate it as a linear system in combination with some disturbance-bounded system, okay? So if I take all of the nonlinear terms and I put them into some extra system and I write my equations of motion in this form, then it turns out I can use the tools we're about to do to search over K using the equations of the linear system to minimize the bound from here to here. And if I have a bound on here, then I can actually say that the whole system is stable even though I only did the control design on the linear system. Okay? I will, next semester, say that more carefully. No, I mean, there's a whole thing I decided not to do, so I'm sorry that I'm just sort of drawing that up, but that is one of the most important pictures, that's the cover of the Robust Control book, right, is like a picture like this, okay? And it uses this machinery to make that argument. It says if you can make a gain, if you can model your system that has an L2 gain here that's smaller than 1, and you can, through feedback design, make the L2 gain of this linear system less than 1, then we know that the loop gain here is less than 1, and therefore the entire system becomes stable. So even though you had an approximate model of your plant, you can just do a disturbance model and say that linear control was enough to stabilize it. Okay, yes?
It seems like an outrageous statement in that we have noise coming in, right? And this thing right here says that given any noise trajectory, the magnitude of noise over time bounds the magnitude of the state error
Yep.
over time in a linear fashion.
Yep.
Which seems amazing if noise can. It feels like it should make it. It feels like it should make it such that noise has to come in linear. Otherwise, if it comes in non-linearly.
You're saying the ability to find this, forget about this picture, or small gains, just this is, as you said, seems like too much.
Yeah.
Mm-hmm.
It's like that says that state changes. The magnitude of state change is linear with respect to the magnitude of noise change.
Not instantaneously. This is talking about this is equivalent, finding a finite L2 gain is equivalent to having a bound on the impulse response of the system. It's the integral x that's going to be bounded, not the instantaneous x. Okay, so it's equivalent to having bounded impulse response to if you were to put an impulse into W, it might go up quickly, but the total energy in that impulse response is bounded. Yep, and then you accumulate those up, and you can get something equivalent here. Yes, great. I love that you're digging into this. This is good. This example is about if I were to use my machinery that was motivated by random inputs, but I say the input is not actually random, it's just unknown, then I can, in this special case, I can recover deterministic stability. But I don't want to mix the fact that when W is random, I can't get x to bound, go to 0. Cool, okay. I hope the discussion was useful, even if I was less precise than I would have been if I had chosen to present that exactly. Okay, so how do we find k to make gamma small? All right. It actually goes through this output, so we're going to use this input-output, all right, and we're going to choose z. So what I'd like to make it to relate it to LQR. Okay, I've got W coming in. I want to design u equals negative kx. U, x is coming out. And I'm going to have some z. I'm going to choose z. It seems a little funny to write it like this, but this is what's going to connect us to LQR. And it's called H2. In a random order. Well, I mean, I know what it is, but I want something like that. Let me find it. if I choose my output to be a vector output, okay, and I'm going to choose it to be this square root of q square root of r times x, then the integral, the nice thing about that is if I choose the integral of then the thing I'm actually bounding is my favorite cost function of all time. Okay, so if I want to say I'd like this cost to be small, proportional to dt squared, then I could try to find something like this. So that's how I'm going to connect it to LQR, okay? And the way it works is actually pretty beautiful. I'm going to write the min over u, the max over w. Maybe I could do it in discrete or continuous time. Maybe it's a little easier. Yeah, I'll just do it in continuous, that's fine. You can even generalize that, and then all of our standard Q is okay. So let's think about what this says. First of all, I'm going to think about rewarding this thing. So I'm going to penalize it for x being away from the origin, proportional to q. I'm going to penalize it for using u, proportional to r. But I'm going to reward it for any time w is big. If you can keep this small while w is big, then that's a good thing. Okay, so I've got a negative here, and I'll choose a positive gamma. Okay. And the optimization I want to do, normally I was just minimizing over u, but now I want to solve this minimax problem. For the worst possible w, find the best u. The order matters, right? Now, it's not too surprising that once I write that as a game, that you get a similar Riccati equation to what we've always gotten. So the same way we take the gradient with respect to u and solve for it, we're going to find this maximum by taking the gradient with respect to w and be able to solve for that in closed form. Right? So I can write the HJB equivalent. That's my Bellman equation. Say it again.
Should all the t's be infinities? Since you ran the time invariant.
Yeah, I guess so. I can choose to do either the finite horizon or not. This is going to be true. If I put a finite time, I should put a partial j partial t. That's what you're pointing out. So you're right. I'll do the infinite horizon just so I can ignore that. Well, it doesn't. Doesn't really matter. I'll just add the partial j, partial t. Good catch. Yeah, if I have a finite horizon, I should really have that. Okay, and the derivation goes a lot like the original LQR derivation. So I'm going to take the gradient of that inner thing with respect to w. And I want to find the maximizer. I'll set it equal to 0. And that tells me the optimal disturbance is actually a simple thing. It gives me 1 over gamma squared Sx. I forgot to say I'm going to assume the j of x is still my nice quadratic form. Turns out to be okay. I can solve for the optimal adversary, okay? And then I can insert that back in, solve for the optimal action equaling 0. It turns out it looks the same as before, but the s is going to be different, of course, given that I'm doing the robust version. And I get a Riccati equation that says S dot is going to be Q plus S, a slightly different Riccati equation, minus 2. I'm leaving off some terms to keep it simple. Okay, this is a Riccati equation. This is complete given everything I wrote on the board. When I said I'm leaving off some things, in general, you can have, you can write a matrix in front of BW or in front of W, and the general version I have in the notes has a few more terms just because I made the dynamics a little more expressive. But given what I've written, I think this should all match. Okay, so the point is, remarkably maybe, you can actually do robust control almost exactly the same way we did LQR, okay, where we solve a slightly different Riccati equation. This gamma that leaks in changes the optimal cost to go and will therefore change the optimal action. Okay, but if you come in and you choose gamma, then you can design a controller that optimizes that objective for gamma. Okay, just in almost identical to the LQR controller. And the cost to go function that you have serves as a dissipation inequality that certifies that gamma is an L2 gain. So this also gives you, not only gives you a controller, but it gives you a controller that's certified to have that L2 gain. Because exactly this is the supply rate that's being minimized. J dot is going to be less than this supply rate. And you can stick that in and see exactly that gamma is an L2 gain for that cost. Okay, does that make sense? I mean, the high level, the detail of that makes sense? I think putting it all together takes some thinking, okay, but it should seem too good to be true. Sava didn't say it this time, but it should seem too good to be true. And here's the thing that is too good to be true. Like, if you ask for gamma to be small, and the system cannot achieve that L2 gain, then the Riccati equation may not have a positive definite solution. So for instance, if I wanted to find the infinite horizon case, I find the steady state solution of this Riccati equation may not have a positive definite solution. As I increase the gain that I'm trying to certify, then at some point it will have a positive definite solution. And beautifully, there exists, for any system that is robustly stabilizable like this, there exists some gamma. And if I decrease gamma, if I found one gamma that works, I'm guaranteed, well, see, if I find any gamma that works, then a larger gamma is guaranteed to work. And so I can actually find the optimal gamma by just solving lots of LQR problems where I make gamma smaller and smaller and smaller until it fails. And that's how you would try to optimize the L2 gain of a system, by searching over K. If you, basically the recipe is increase gamma until you find a positive definite S, okay? Then decrease until it fails. Like you could, I do this like, I just double gamma or something. You just keep it bigger and bigger and bigger. You basically do a golden section search to try to find the smallest possible gamma. And what that, I hope, almost very familiar math does, I mean, you can just call LQR with a slightly different cost function, okay? What that slightly, and you call it many times until as you decrease gamma, you're searching over a K that is optimizing the L2 gain, and you are now doing H infinity control. This is one approach to H infinity control, if you've heard of that. H infinity robust control. So the H stands for Hardy space. This is the Banach space, the Hardy spaces. There's a lot of math behind that statement. The H infinity norm of a system is actually the L2 gain is the H infinity norm for the system for some particular input output. So finding the smallest H infinity gain is equivalent to finding the smallest L2 gain. And this is one approach. This is the most familiar I could generate approach to H infinity design. I think almost all of them require some sort of line search kind of piece of component. Yeah?
When the Riccati equation solver fails, do you get like any sort of information you can use to like guess a step size for the next one, or do you just have to treat it as a black box?
I have always treated it as a black box. It's possible that there's more information. The search space is scalar, so it doesn't need to be super smart. Yeah.
What if we can control R as well? So like increase gamma and increase R.
Mm-hmm.
Is there anything you can say about like what like gamma can take? And I'm guessing it depends on like the structure of B as well.
That's a great question. I don't know. Some nice statement about that. It might exist, but certainly that search space would be bigger, and you could find different gammas for choosing different R's. I completely agree with that, but I don't know that it has particularly nice properties for search. Yeah, it's interesting. So if I had answered less questions on Piazza last night, I would have brought in a simulation showing this doing something qualitatively different than the standard LQR. But it actually takes, I tried, it just takes some work because I think, oftentimes this will do LQR-like things. You have to actually think pretty carefully about how to construct a system that this robust controller acts really qualitatively different than the LQR controller. I mean, the analogies are clear, but there's certainly, remember the John Doyle abstract saying there are no guarantees for LQG control. This was the answer to LQG control, was doing robust control and having systems that can give guarantees. Right? There are definitely systems where this changes the guarantee. It gives you stronger guarantees on performance, right? But it even changes the control gains you'll get out. It just happens that the cart pole and stuff like that don't show it very easily. I could take one of the canonical systems, that would be fine, but I wanted to show a cart pole or something. Yeah?
Like, how practical is this? How often would people use this rather than just regular algebra?
Yeah. No, I think, so because of the strong guarantees, he puts it in a different class. You could think of this as a guaranteed, this is a contract on guaranteed control performance even when you have a noisy input. As long as you have a model of the noise that's coming in, right, you can say, I'm going to certify the gain of that performance. Right, so this puts me in a different space in terms of the confidence I can have in the system. The question is really just how much does it change the gains you're actually running? Or is it just a nicer analysis, right? Yeah, I think there are great examples of where it qualitatively changes the gains. I'll try to construct one. Okay, let me say a few words about how we would use the same kind of thinking for trajectory optimization, yeah? Unless there's any other questions about that. Okay. We talked about stochastic trajectory optimization last time, where we rolled out, the simplest version I gave you was rolling out many different trajectories and just taking the expected value and using that in your direct collocation or whatever. There's a picture, I'm thinking of the 10-minute version of this now. There's a picture of what you can do in the robust control version of that. And again, when the dynamics are linear, things are clear, and actually when they're nonlinear, there's natural extensions that follow from what we've been doing in class. Okay, so let's just think about first doing the sort of trajectory optimization version of this, which was remember the first thing I did to motivate trajectory optimization was just doing the linear MPC, and we got a quadratic program to solve LQR along a trajectory. Okay, so we can do very similar things here for trajectory optimization. But if I'm doing a finite horizon case, then then I can put myself in maybe a slightly different situation where I'm willing to say W is bounded. Maybe my initial conditions are bounded. So my setup is a little bit different. So I'll say Wn comes from some fixed bounded set of possible disturbances. Okay. Again, robust control, the philosophy there is not so much that I'm being conservative because I put limits. It's actually, I don't feel that it's practical to have to certify the exact distribution of W. Just saying it could be anything seems like a nicer requirement. I could say that x0 is drawn from some element of some bounded set of initial conditions. And I'd like to somehow write a trajectory optimization that thinks about not only the nominal x and u, but maybe the worst case. Like what are these objects going to do over time? Where are the possible states that xn could possibly end up at in some future n? So I think the natural question that comes up in these kind of settings is for what choices of, let's say, x and w can I tractably propagate x, let's say n, which would be the worst case set of possible states that I could be in at time n. The picture, if I were to draw my Beggar's Canyon thing again, got my little airplane down here. Okay, if I have some initial distribution of possible airplane locations, I'd like to find some trajectory, let's say, where I can think about all of the possible states that I might be in after one step, all the possible states I might be in another step, and I can write constraints of the form that if the entire set here stays outside of my obstacles, then I'm going to be pretty happy with that trajectory. Okay, this would be called tube MPC. Or robust, there's very, robust MPC is overloaded. So tube MPC is probably the most, will most likely, a Google search on that will most likely give you pictures like this. Okay, and you can sort of guess the answer to this question for when the dynamics are linear or are linearized around some nominal trajectory, as you're doing trajectory optimization, for instance. There are kind of two natural answers to what the right representation is. The first one is to choose polytopes, and you can propagate polytopes through a linear system pretty nicely. The other one that goes pretty nicely is ellipsoids. If you choose quadratic, the subsets of a quadratic function, then you can propagate those through. The polytopes, they both have, they both require bounds and approximations to make that work. The ellipsoids tend to lead to semi-definite outer approximations, and the polytopes lead to, in the best case, linear programming approximations of what those constraints would be. Okay, and you can kind of see that because if you think about what would this look like if I were to say now x of even 1 equals a of x0 plus bu, if I'm about to choose u at time 0 in order to optimize some objective, I can sort of write the set version of that equation. If I think about the set of possible x's, the set of possible w's, I'd like to find that x1, I want to understand what this new set is going to look like if I take this set and propagate it through these linear equations. And this is basically, if I have a bunch of polytopes here and I multiply them by some linear matrix, that's just a rotated or something polytope. If I add them together like this is just adding a constant for some choice of u. This is if I'm adding two sets together, that's done with the Minkowski sum of these two sets, and I get another polytopic set that comes out. That's exact and precise, but the set that you might get if you just do this, let's say I describe this as a polytope with 4 faces, and this is a polytope with 6 faces or something. You know, I might get a lot of faces on this one. I put it back here. I add in another 4 faces. The description length of the true polytopic set can grow very quickly. So the reason that the approximations come in is if you try to find an outer approximation of this set with a smaller number of polytopic faces, then you can write those with different optimization-based relaxations. Okay. Similarly with ellipsoids, you could propagate them through, but you end up writing typically SDPs, I think, to solve those. So you can use those objects and just propagate your decision variables in your trajectory optimization become the faces of my polytope. The containment condition becomes the dynamic constraints. And then I can write constraints like I don't want my polytope to intersect with my obstacles. And that becomes a way to do sort of robust trajectory optimization. It can be very conservative. And someone, I think Sam asked this last time, was that you can do better in the robust MPC if you search over not only a nominal u, but a feedback gain. So let's say u and k for every step. You can definitely do better with that. But these can be potentially conservative. If you're piloting an autonomous car or something, it could be that conservatism is good. you know, but there's a powerful set of tools that follow that lineage. Sums of squares would be the natural nonlinear generalization of that. You can take most of the things that you would write in the linear setting and write the semi-definite relaxation of that. You'd get a sums of squares kind of program. And you can do all these things with sums of squares. But I would say that the linear versions of them tend to be tractable enough that you can do it directly in the optimization. And depending on the order of your sums of squares or whatever, that has tended to be an offline after the fact optimization. Yeah?
Related to what you were just saying, is this approach able to include the possible deviations that you get from an open loop control approach as you were going through this trajectory, or like, yeah, is that included in that range, or is it still assuming that you're kind of sticking with what's
So it's a good question. Yeah, I think you could see it. I hope you can sort of see it in these equations right here. So if I were to put in, you know, u nominal minus k x0 here, then that would just be a different propagation of my sets in the equations. If I can search over k and u, that will propagate different sets. The sets will tend to be smaller if you're also allowed to do this, in terms smaller in volume. Yeah, but the propagation can be certified and correct both in the nominal u case or in the feedback case. It's just about lifting the linear equations of a vector that goes through to the linear equations of a set that goes through. And they're very powerful. They really, I think there's extremely good tools in that lineage. That was a little less time than I was going to spend on that, but okay. Yep.
Is there a continuous interpretation of this?
Yep. Let me think about the right way to say that, but for polytopes, that seems ugly. I don't know how to do that for polytopes, actually. I hadn't thought about that. I think for ellipsoids, it should be okay. I don't actually know what I'd write down immediately. That does sound like a harder question. Normally it is discrete time, but there should be a natural continuous time equivalent. Yeah. Okay, good. I'll stick around for a few minutes with projects, but I do actually have to catch a train in a few minutes, so I can't stay super long.